The I can statement for this is I can calculate rate of change and identify it as constant or variable. And so a rate of change, when we're talking about linear equations and graphs, has to do with what the graph looks like. And down here is more of a mathy definition. It's a ratio of the amount of change in the output to the amount of change in the input. Remember, we can measure change through subtraction. So, for example, if I want to know how much difference or how much change is there from 3 to 10, I can go, okay, 10 minus 3 is 7. So it changed 7 between 3 and 10. That's just one little example. But this might make it a little more clear. We express the rate of change as a fraction, and the change in the output or y values goes in the numerator, and the change in input or x values goes in the denominator. In other words, we say change in y over change in x. And one formula that I want you to write down, because we're going to be using it a lot this unit, is y2 minus y1 over x2 minus x1. And I'm just going to comment on this really quick. What this means is if you go to a graph and you look and there's a point x and a point y, and then there's another point on that graph, point x and point y, you can plug in the values of these points into this formula to figure out the rate of change. And in this case, we would call this x1, and this would be x2, this would be y1, and this would be y2, because we have two x's and two y's, so this is the only way for us to differentiate or tell the difference between the x's and the y's. That's going to maybe seem kind of fuzzy right now, but it's going to make more sense when we go to an example. But let's keep in mind what we're doing here. We're trying to put a number to a rate of change in a graph or in a table. So the first thing we're going to do is we're going to look at some inputs and outputs. We're not even going to look at the graph, but we're going to come up with some ways to figure out the rate of change. Then we're going to end with an example where we just look at a graph. So in this first example, it says Eves keeps a record of the number of lawns she mows and the money she earns. So in day 1, for example, she mowed 1 lawn and earned $15. Day 2, 3 lawns, $45, so on and so forth. And the question becomes, is the rate of change constant or is it variable? And here's how we might consider a way to figure this out. First off, remember the top part of the table here, the inputs, are x's. The bottom part of the table here, the amount of money earned, is our y's, or the output. And so when we look at this, we want to put, when we're trying to calculate the rate of change between, let's say, day 1 and day 2 first, we want to put the change in money in the numerator, okay? And in the denominator, we want the change in lawns. Because remember, back here in the very first part of the lesson, we said the change in y goes in the numerator and the change in x goes in the denominator. Let me comment further here. So the change in money happens to be our y, so that's got to go in the numerator. And the change in the number of lawns happens to be our x, and so that has to go in the denominator. So this table, we actually are switching which one's in the top and which one's in the bottom. And so here's how we consider the changes. Here's how we figure out, the math, I guess, behind it. Is from day 1 to day 2, if you look at day 2, this x, you could call this x2, and this would be our first x value. Okay. In this case, this might be our first y value, and this would be our second y value. So if we plug those into that formula that I showed you earlier, this y2 minus y1 over x2 minus x1, we get 45 y2 minus 15 y1 over x2, or 3, minus x1, or 1. Now at this point, it doesn't matter whether we would call this x2 and this y2 and this x1 and this y1. It doesn't matter as long as we're consistent within the points themselves. In other words, if I call this x2, this has to be y2 because they correspond to each other. 15 is the output for 1. If I call this y1, then this has to be x1 because 45 is the output for 3. But I chose to call these 1s and these 2s. So, in essence, if we were to graph these as points, we would have the point x1 and y1 on a graph, and we would have the point x2 and y2 on the graph. And when we go to the graph, it's going to make a little more sense. Right now, we're just working off of a table. So if we continue the math on this, it's just a simple matter of simplification, and we end up with 15. 45 minus 15 is 30. 3 minus 1 is 2. And so that gets us our 15. Now, let's look at one more thing here. We're going to do a few more of these to make this hopefully make a lot of sense to you. Let's look now at the change between day 2 and day 3 in our table. First, let me comment that our change was a total of 15. That's how we express our change from day 1 to day 2. But from day 2 to day 3, we do the same thing. But notice the numbers are different. In day 3, in the amount of money earned, my y2 value, or the second y value, would be 90. The first y value would be 45, or day 2. And so we do the subtraction in the numerator. Similarly, in the denominator, we have our x2 minus x1. Okay, and when we continue the math on that, we get 45 over 3, or 15. And yet again, we use this equation of y2 minus y1 over x2 minus x1. And notice the changes here are the same. Let's do one more, and I'm going to talk about it in a slightly different way, in case this hasn't clicked yet. Let's continue this task, but this time, let's find the rate of change from day 3 to day 4. Okay? Notice in day 3, this is our x, and this is our y. To day 4, this is our x, and this is our y, our input and our output. I'm going to just call this x1 and this y1 because it's the first one I see in the table when I read it from left to right, and it's the first day in our list here. We want to find the rate of change from day 3 to day 4. So that means this must be x2 and this must be y2. And when we plug those into this equation right here, we get this value. Yet again, 15. When we plug in all of the numbers. And really, this is just a matter of matching. So you take your y2 and you put it in for y2, 120. You take your y1, you put it in here, and so on and so forth, and you get your answer. The same thing can be done from day 4 to day 5. We plug in those numbers using this equation, and notice we end up with 15 again. So in this table, coming all the way back to the very beginning of the problem, we found the rate of change from day 1 to day 2 to day 3, day 3 to day 4, day 4 to day 5. And the rate of change, or the change itself, was the same in each particular day change. So what does that mean for us? Does that mean that the rate of change is constant, or does it mean it's variable? And that's what I want us to consider now. Well, since we know it was 15 for each day, we say that the rate of change has to therefore be constant. The word constant means without change. I shouldn't say without change. Constant means it's not variable. Let me think of a better way to say that. Something that's constant is consistent. So it's a constant fact that our bell rings just before 7:30. It happens every day. So it's a constant thing. A variable bell will be where it would ring at different times every day. That would be variable. So because our rate of change between all these days was constant, we say that the rate of change is constant. If this wasn't 15 and this one was 15, let's say this one was 13 instead of 15, we would say that the rate of change was variable. But in this case, it wasn't. Let's do one more example, and I think this last example is actually slightly easier because we at least have a graph to look at. Okay, so let's take a look at this. This is the last example. The graph shows the distance Nathan bicycled over time. What is Nathan's rate of change? Find the rate of change from 1 hour to 2 hours on the graph. Notice the x values here are in hours, and the y-axis here is in distance. Also, notice we're going to use this equation yet again to find the rate of change. And so, if we take our 2 points here, we have point 1 and 15 at hour, hour 1, okay? And at hour 2, we have the point 2 and 30. Okay, I'm going to say this is going to be my x1 and my, and my y1. Let me fix that. And I'm going to say this is going to be my x2 and my y2. The reason I'm going to say that is just because this point comes after this point if I read the graph left to right. So I plug in the numbers. y2 was 30. y1 is 15. x2 happens to be 2. And x1 is 1. When we do the math, we get 15 over 1, or 15 miles per hour. So that means the rate of change from the first hour to the second hour was 15 miles per hour. And notice, if I asked you, how far did Nathan go in 1 hour, you could look at the graph and go, oh, at time 1 hour, he went 15 miles. At time 2 hours, he went 30 miles. At time 4 hours, he went, or 3 hours, he went 45 miles. So the rate of change from 1 hour to the next is 15 each time. His distance increases by 15 every hour he travels. Let's take a look at one more possible example. What if we wanted to find the rate of change over a larger span, so from 1 hour to 4 hours? Well, this equation would still work. We look at our 2 points. Our point at hour 1 was 1:15, 1 and 15 here. And at hour 4, the point is 4:60. We follow the same strategy. We can call this x1 and I did the same mistake again. x1 and y1. And we can call this x2 and y2. Because when I read this graph left to right, this point, 1:15, comes first. So those are going to be my first x and y, and my second x and y are going to be the last. I plug in the numbers again. So y1 in this case, let's see. Or I'm sorry, y2 in this case, because y2 comes first, was 60, and y1 was 15. And my x2 is 4, went here, and my x1 is 1. So I do the math here, and I get 45 over 3, and 45 divided by 3 is 15 miles per hour. So this also means then that the rate of change is constant, because the rate of change between hour 1 and 2 is 15, and the rate of change between hours 1 and 4 is 15. So the rate of change is yet again constant. So the question might be asked, can we tell if a rate of change is constant just from looking at the graph? And the answer is a resounding yes. Yes, we can. If it's a linear equation that is a non-vertical straight line, it's going to have a constant rate of change. Because of that constant rate of change, it is a line. So there's a quick shortcut for you. If it graphs a straight line, if it looks like a straight line, the rate of change is constant. To calculate the rate of change on a straight line from any point to the next, you simply take 2 points and you plug them into this equation we've been using this whole lesson. Now I understand this equation's new, and so we're going to be doing some things in class besides just this video lesson to help it all make sense. But I want to come back before the end of this video to the first example problem and point something out. Just like in that graph, where we chose our 2 set of coordinates to figure out our x's and our y's, in this particular problem, for example, from day 3 to day 4, we did the same thing. We chose what our x1 and our y1 were going to be, and we chose what our x2 and our y2 were going to be. If you accidentally switch these around, it wouldn't change the math. It would still come out right. So anyways, good luck to you. I know that you can do well. Use this formula to help you on the worksheet. And also use your knowledge of what we're doing. We're trying to figure out the rate of change, or what's going on from one point to the next in a graph or in a table like in the first example. Best of luck to you.